Okay, now let's turn into your note packet to example number 3, and we're going to go over a couple of these problems together. You see in example number 3, they're going to give us one region to work with, and then we're going to find the volume of 6 different solids based on revolving the region around 6 different axes of revolution. So let's get started. Example number 3 says find the volume if the region enclosed by y equals x squared. Let's first go to our first graph and sketch a picture of y equals x squared. And then we'll get a parabola that goes to the origin. This is just a rough sketch, there's no grids. We're not going to be extremely accurate. And then they say y equals 0. Remember, y equals 0 is just another name for the x-axis. And then they tell us the third line is x equals 2. So we'll draw a vertical line like so. And now let's identify the shaded region that they're dealing with. It's this little region in here enclosed by all 3 graphs. Okay. Well, now we can go to work. They want to find the volume of the solid of revolution created when this region is rotated around. And in part A, we're talking about the x-axis. So if we go, identify the x-axis as the axis of revolution, we're going to be able to determine here, without trying to draw a 3D model, whether we're going to use a disk method or washer method. In this particular problem, we're going to use the disk method, and here's how you can tell. The shaded region is adjacent to the axis of revolution. There's no gap, there's no empty space between the shaded region and the axis of revolution. So you can tell if we were to rotate this region around the x-axis, the cross-sections would be solid circles. Okay. I guess the first thing we can do is go and identify, we don't need the little radius, we're going to cross that off. And to identify the big radius, it helps to draw a picture on the grid, on the graph. And it's important you understand, we start drawing a radius from the axis of revolution. It doesn't matter where you go, pick anywhere inside the shaded region. And now we're going to go from the axis of revolution to the far end of the shaded region. This is going to be our radius. And again, we're going to say top minus bottom. So in this case, the top of our radius segment is defined by the curve y equals x squared minus the bottom. The bottom of our region is defined by y equals 0. So our radius is just x squared. The exponent didn't turn out too well. Let me write it so it's not on the line. There we go. Okay. Now, to find the volume of this solid, here's what we'll do. We're going to say the volume is going to be pi times the integral from 0, the origin, to 2, x equals 2, the radius function squared, x squared squared. We're not going to evaluate the integral right now. We're just going to set it up. Okay. Now what we should do is pause the video and just sketch this graph in the next box, and then we'll come back and go over the setup together. And now in this case, if you take a look, we have our region defined, our region is shaded, and now you see we're going to go around the axis of revolution, y equals 4. So the first thing that we want to do is we want to figure out if we can use disks or washers. We can tell, without even drawing a 3D model, that for this case, we are going to use washers. So here's how you can tell. The axis of revolution is the red line. The shaded region is shaded in blue. And you see the big white space right here? Right here. The space between the shaded region and the axis of revolution is what will make a hole when we rotate this thing, when we rotate this region around the axis, y equals 4. And we need 2 radii. Let's identify the radii. First things first, we're going to start at the axis of revolution and go to the far end of the shaded region. This is how we'll define our big radius. From the axis of revolution to the far end of the shaded region. And let's set up our expression. What's on top of the axis is 4 minus top minus bottom. What's on bottom of this radius is 0. So the big radius function is going to be defined as 4 minus 0. Now, that's just 4. Now the little radius function, once again, we're going to go from the top of the shaded region, this time to the near end of the shaded, we're going to go from the axis of revolution to the near end of the shaded region. That's how you set up little r. Now our expression can be found by figuring out what's on top of the little radius segment. The top of the little radius segment is the horizontal axis y equals 4 minus what's on the bottom of the little radius segment. Well, the bottom of the little radius segment is defined by the curve y equals x squared. Now we can set up our volume expression. Our volume is going to be pi times the integral from 0 to 2 of first the big radius squared, 4 squared, minus now the little radius squared, 4 minus x squared, quantity squared. And of course, we'll complete our integral with respect to x. Okay. The hardest thing to get used to is identifying the radii, coming up with the expression for each radius. And once we do that, I think you're going to find these problems are all just the same type of problem, repeated over and over and over again, with a different context, with a different expression, and that's all. When you're ready, let's pause the video and draw a region for problem number part C. But to make it more interesting, guys, before we do anything, let's change this from the line y equals 5. Let's make it the line y equals negative 5. Okay, so keep that in mind when setting up your region. Once you're ready to continue, go ahead and press play. But pause the video now and draw your graph. Oops. Okay, now taking a look at example 3, part C, I decided to go to some scratch paper because Stu doesn't always give us an awful lot of room to work. So we have our shaded region drawn as we have before. It's the same region we've worked with in part A and part B. Now we're going to rotate our region around the horizontal line y equals negative 5. Remember, we changed the axis of revolution from the packet to get a different look. Now, we need to identify if we're going to use discs or washers. And we can tell from inspection that we're going to use washers because there's a big white space right here between the shaded region and the axis of revolution. With this, we know we're going to need a big radius, and we know we're going to need a little radius. So let's start identifying. To identify the big radius, we're going to draw a segment from the far end of the, I misspoke, from the axis of revolution to the far end of the shaded region. Okay, that's our big radius. And now let's set up our expression. We're going to do top minus bottom. What's on top of this big radius segment? Well, it's the curve y equals x squared. Minus what's on bottom of the radius segment? That's the horizontal line y equals negative 5. So our radius is going to be x squared minus negative 5. Or in this case, we'll clean it up, and we'll just call this x squared plus 5. Okay. Now let's go identify the little radius. To identify the little radius, we draw a segment from the axis of revolution to the near end of the shaded region. Now we'll set it up with top minus bottom. What's on top of the radius segment? That's y equals 0. What's on bottom of the radius segment? That's y equals negative 5. So we can clean this up and say the little radius is just 5. Okay. Now, just a reminder, to set up our integral, with washers, you know that we're going to say pi times the integral from a to b of the big radius function squared minus the little radius function squared. Now let's get specific. In this case, our volume will be pi times the integral from 0 to 2, the big radius function, quantity x squared plus 5, squared, minus the little radius, in this case 5, quantity squared, with respect to x. And there you have it. We've set up an integral to find the volume of the solid of revolution. Once you get used to drawing the radii and setting up the radius expression or radii expressions, You can find these problems aren't that difficult to set up. Okay. Now, that's going to end it for this video. The next video, we'll go on to look at parts D, E, and F of example 3. Thanks for watching. Hopefully this was helpful.